Hello, everybody. We're going to change gears a bit. Before I start, I was just going to ask a couple of quick questions. How many of us care about carbon footprint and climate change? That was a kind of silly question because nobody's going to say no. How many of us think we live a carbon neutral life ourselves? How many people even know what's our carbon footprint? That's essentially the theme and the topic of this talk. Like, how do we measure carbon footprint of our, at least professional life? Most of us are computational neuroscientists, if you're at OHBM, and it's how do we try to reduce it? So I'm not going to try to make this a depressing, sad talk, but more like a positive approach on how can we look at this problem and how can we solve it ourselves. So yeah, don't run away for the possible problems. Cool. I should mention that this work has been done a lot by Nikhil, who unfortunately couldn't be here, partly because he didn't want to add to his carbon footprint, so all credit to him. But yeah, and both of us are part of CSIG, which is Sustainable and Environmental Action Group at OHBM, and that's kind of my disclosures. I'm also part of Open Science Bubble, so usually my thinking process derives from open science and now sustainable science. Cool. So mostly we can talk about four things, like the stakeholders in this who are part of the problems and also can be part of the solutions, the sources of carbon emission in neuroimaging research, and how do we calculate the footprint, and also what can we do, which is the key aspect of this talk. Cool. So most of us like XKCD comics, so I thought I should start with one. And this is something caught my eye because it's kind of, the problem we're trying to solve is almost a recursive problem because we are part of the problem. And essentially, more research we do, we are contributing to the carbon footprint as well. So we have to think, it's very tricky to think about it and also solve. So that's what I was thinking when I was looking at this cartoon. And it's hopefully most of us can relate to this sort of mindset. So yeah, most of the slides here and most of the things I'll show here are coming from the 3 papers that we worked on together. And if you're interested, you can read more about those in these on these QR codes. And we are basically providing people ways to think about how we think about carbon footprint of our research and what can we do about it at different levels. Talking of levels or different stakeholders, this talk can be helpful to many different people. If you're a trainee, what we really want to do is just like open science has been doing for a long time to adopt open and fair practices. We're trying to instill sustainable research practices as you're starting as early as possible. For the PIs, we are trying to hope they will think about sustainability and carbon footprint as they build their research data management plans in their labs and beyond. And for Institute, I think it's the much bigger picture problem. How do we actually build green infrastructure? Because in the end, it's the infrastructure that will play the biggest role. Talking of, broadly speaking, there are 3 different ways you can think of how the carbon emissions are created in our research. It can be from data storage facilities, data compute facilities, and also data transfer. Given the time and the scope, we're mostly going to focus on the storage a bit and also primarily on how to reduce the footprint of our compute. Just briefly about storage, because it's the easiest to think about and easiest to understand. What we think about data storage has happened over the last few years is the rebound effect. So if you've realized over the last 20 years, the cost of the silicon, essentially, our silicon-based storage system has fallen extremely low. That has caused much higher use. Everybody has terabytes of data, either locally or in their Google or Dropbox or iStry or P-Drive type of things. And we just blindly back up everything, and there's a huge amount of storage footprint that every individual has. And if the individual has multiple terabytes of data, personal data, just imagine how much data we are creating in our research in petabytes of data. And it's all good overall if we are using all of that data, but unfortunately, most of that data is dark data, which we just do it once and never even see it again. It remains in silos, and there are other talks in this in the educational course that talk about it more. And there is junk data that we also create while doing some sort of processing, and again, forget about it and never use it again, but it gets created into your work directories or temporary directories, and that gets, that accumulates over time in a large silos. So Nick, who was another co-author of this talk, has created a tool. It's called fMRI Prep Cleanup. So if you've used fMRI Prep, it's basically a fantastic pipeline to do functional imaging processing and analysis. But during its whole life cycle of that thing, usually you create a huge amount of files, and based on overall surveys and analysis that we did, it's 95% of it is never used again during once it's created. So there's a tool if you like to try. It's called again fMRI Prep Cleanup on the GitHub, and you can try to use that tool to clean up your data. Moving to compute, which is usually the biggest culprit in the carbon footprint of our academic research. Again, briefly or broadly speaking, longer the runtime you have, more footprint or more carbon emissions you have. There are other calculations that go into it, which I will talk in a second. But if you just really want to remember the hand-wavy stuff, that's going to be the case. Talking of AI models these days, which are getting more and more popular, not just with the LLMs and stuff, but also in our neuroimaging research. What happens is training takes long amount of time, so that usually takes huge amount of carbon footprint, whereas inference usually is fast. There are some caveats to it. But again, the point here I'm trying to make is we are not trying to say everything we do is bad, including AI models. There could be good cases for AI models that can help you reduce the footprint depending on the use case and how we think about it. A more traditional way of thinking about, more traditional concerns about inefficiencies in neuroimaging would be how we code things. And most people in the neuroimaging community are not software developers, so we tend to write inefficient code. We use a lot of GPUs and scientific toolboxes which are not optimized for sustainable computing. So those are another considerations people should have when they're writing computing, working with compute. There's another slightly simpler, but also the problem of when things become easy, they become very prevalent, is the huge amount of duplication we do with our processing pipelines. So every new student that comes to the lab will try to process the same thing again and again, and what it creates is what we call the multiverse of pipelines and multiverse of process data, and that accumulates a lot of storage space as well as uses the compute unnecessarily. So some of the big examples of the compute footprint actually come from genetics. So if you're doing a GWAS on UK Biobank, which is one of the largest data sets for genetics analysis, it actually consumes over 7.5 flights from New York to Melbourne. So it's pretty large. If you have not seen the compute footprints before, I was very surprised when I first saw how much the actual footprint of the compute is. And this is something, again, goes back to trying to coordinate computation in a way that it happens on the more of a greener compute centers, as well as happens with less duplication is one of the ways we should try to look at this. I was not going to put AI before, but until last year, we were not talking about AI much, but these days, everybody uses AI, even if you are not working on AI research. Everybody uses some version of LLMs for their daily research. And if you thought GWAS is doing a lot of carbon, LLMs are much worse. So they create a huge amount of carbon emissions. And so one example I think was getting more popular these days, I think because of the social media coverage, was like when you say please or thank you, ChatGPT consumes like huge amount of carbon. And again, I saw this picture recently about it actually consumed electricity that Australia uses for a day and a half, which was also fascinating in terms of the scale. Okay, so more concretely, we also did some experiments, again, with neuroimaging pipelines. What we try to do here is run different variations of how we can run fMRI prep pipeline. So P0 is the default run of fMRI prep, and then you have multiple options that you can try out when you're running fMRI prep. So there are from P1 to P7 are basically different variants on, for different types of analysis. And I won't go through all of them here, but the paper, if you wanted to take a deeper look, is available. And again, Nick is from the UK, so he likes to do Google Maps durations and lengths in UK. So if the default, fMRI prep takes about 7.5 kg of carbon or 43 miles in Portsmouth. Whereas if you don't run free surfer, which is almost cuts down in half. And if you do use high resolution templates, it almost doubles. This is just a way to show that different settings will have different impacts. Of course, depending on your analysis needs, you may have to do one versus the other. There is no, maybe there is no option for you. But again, this is a way to basically raise awareness on what the tools you're using, how they affect the footprint, and maybe work towards making them more efficient. We also did another paper where we compared different neuroimaging pipelines with each other. And it turns out FSL is one of the most efficient ones amongst the three that we compared. But again, this is, just to raise awareness and how to look at how to compute the carbon footprint and not say one is better than the other, because each software has its pros and cons. fMRI prep usually has been containerized well and used extremely effectively in the research. But again, this tells you how do we measure these footprints, and we can work towards reducing those. So just broad recommendations at an individual level. So if you see on the top there, usually I put the stakeholders who can think about these problems and benefit from those. If you're not using FreeSurfer, don't turn on the FreeSurfer flag. There are a bunch of other things you could do to make it more compute effective if you're running it for some testing and trials. And again, there's a paper that talks about this in more detail, and you can feel free to check it out if you want to know more. Okay, I haven't really talked about how we actually calculate the footprint yet. So that's next part of this talk. For computation, usually we calculate footprint based on the CPU and the memory usage, and both of them create different levels of carbon or emissions based on their power draws from the motherboard. But then that factor gets multiplied if you're on the cluster. And if you're running multiple, basically compute nodes in the cluster, there is a factor called power use effectiveness. So if you are running a cluster in Australia or in Canada, where I'm working, so we have a cluster called Compute Canada. So all of these clusters have usually published their PUE, and that plays a role. So lower the PUE, the better it is. So in Quebec, it's 1.2. That means your HPC cluster is slightly more optimized than something that would be higher than 1.2. Usually it ranges between 1.5 to 1.7, that type of thing. But you should always strive to make it lower by improving your hardware for the clusters. And the third factor that really affects the carbon footprint is unfortunately where you are living. So the carbon producing energy infrastructure or the coal or something like that will have a much bigger impact on the carbon footprint, and that basically depends on the energy grid that you have. And that factor is actually called carbon intensity, so that's a third factor that plays a role in your overall carbon footprint. There have been a lot of initiatives all over that try to measure and calculate the carbon intensity factor for different parts of the world, either at the national level or even at a state or provincial level. And this is one of the maps that I think I did last week, so it's pretty recent. So you can see different parts of the world will have a much different carbon intensity profile. Okay, so putting this together, the total carbon footprint is basically the energy consumption that is done by your compute hardware multiplied by your infrastructure's efficiency, essentially. And you never have to do this by hand. There are now tools that lets you calculate this automatically. And one of those tools is called Carbon that lets you calculate carbon footprint depending where you're located automatically for you. And so what we did is a couple years ago, I put the code Carbon as a part of fMRI prep. So if you use fMRI prep, you can have these flags, and you can use these flags to calculate the fMRI prep footprint when you're doing the run. And you can change this based on which country or which part of the world you are in. This is already part of fMRI prep, by the way. The next part is, again, the fMRI prep is like the tool that is embedded, the code Carbon is embedded into that pipeline. There are more generalized tools, browser-based tools. One of them is Green Algorithms. And if you have your phone right now, you can actually go on this website and basically try to calculate the footprint. This is more of a broad level approximation of how things will work. But it's still pretty good. So it's not actual one that they measure during the run, but it's an estimate that you get before you run, which could be also useful when you're doing large-scale studies. And so if you have time at the end of this presentation, I would encourage all of you to go on this website, and it's literally putting a few numbers there that you can try to see. And nowadays, they also have another page that is meant for the AI models. So you can also calculate the footprint of your training and also your inference. And that's super useful because based on where you are, if you have option to choose a different cluster, you can then pick a different cluster to train your models, and also different time of the day, because both the location and the time play a big role for the carbon footprint. More on the actual scheduling part on how to do this instead of manually. There is a really nice tool called CATS. It's called Climate Aware Task Scheduler. So if you're familiar with Slurm or SGE type of schedulers, this tool basically helps you schedule jobs at an optimal time when your footprint might be lower than you just send it blindly. Again, it's based on, it's a Python tool, and it works with both SBatch and QSub. So if you just go on the website, they can also give you like almost like a weather forecast. They can give you a 2-day carbon intensity forecast on when it would be better for you to submit the jobs. It's a very nice tool to have if you're doing this at a large scale. There's a demo. Hopefully it plays. Do I ask somebody to play this? Oh, cool, it was working. I hope the resolution is big enough, but like I said, it's a simple Python repository. Unfortunately, right now, for the location part, it only works in the UK because UK has the grid data available live. So they pull the live electricity grid data to find the optimal time and location to submit jobs within the UK clusters. There have been some PRs for other countries, and I encourage you to do one as well if you want to make it work for your country. So again, they are definitely looking for the collaborators to make this into a global tool. So yeah, but again, it basically tells you if you run it right now versus if you run it at optimal time. This is basically showing you will reduce your footprint by more than half. And again, this can be automated by embedding this into a Slurm as well. I think he's going to show that quickly. Or maybe this is SGE, but is this visible at the end? People can see? Okay. Also, I just like the logo. It's pretty cool. Great, so I think he found the time. If you guys missed it before, there was optimal time and day, and that's what he's inputting right now. The 2024 May 17, and then that's the script that gets submitted, and then you can see, and it will be submitted at that time. So it's pretty easy to use, honestly. Again, and if you have some sway over your HPC people, you can also ask them to incorporate this directly. Cool. Going forward. Okay, so yeah, I'm almost at the end. What we're really looking for now, there are a few tools, like I said. There is a cleanup tool for the data. There's a tool to calculate your own footprint using code carbon or green algorithms, and there are tools to basically optimize your compute runs, which is the CATs. But again, all of this we do on the side with very little time and resources on this. So we are really hoping people will contribute to make these tools more widely used and widely supported. And we are not the only ones. Many people who work on the workflow engines, for example, Nextflow is one of those getting popular workflow engines. They're also looking at embedding this into their code, where you can actually estimate the energy consumption for each pipeline task. And so it can optimize at the task level and not just the end-to-end workflow level. So all of this is pretty cool. So the takeaways for, again, the three stakeholders I mentioned in the beginning, the trainees, if you're a trainee or a PI or institutions, the simple things we can do, it's just like how we have been telling people to recycle for a long time, adopt green practices in your daily life. It's the same goes with your digital life as well. So don't be a data hoarder. We are all, I think, guilty of that, including myself. Try to be more efficient. The second thing is actually the way more important thing, and we have a next talk that will also talk about this a bit. One of the easiest things we could do right now is to share process data. So most people, if you share process data, that fits back into the open science theme of this educational course as well. There's always been BIDS, so BIDS helps you standardize and share raw data, but we also need standards and ways to share process or derived data or IDPs, because if they share those IDPs, other people don't have to process the same exact thing multiple times. Do try to be aware of which tools you're using, and if you can report your carbon footprint, that would be great. I think if you've seen I think airlines and the trains do this all the time these days to raise awareness. They'll post how much carbon footprint their flights or trains are taking. And if you're a developer, try to incorporate what we call a green mode of computational pipeline if you can. For the PIs, again, support more greener HPCs. Be aware which HPCs are greener than the other. If you're in committees that can have some say in building data centers or compute centers or clouds, promote efficient data centers. And especially encourage to, again, going back to the previous point, if the entire lab, especially labs that generate a huge amount of data, can share the process data with other people or somehow centralize some of the processing that can help. And I guess the BrainLife and NeuroDesk would be great tools for those as well. We would avoid duplication of a lot of compute. And if you are institution's director here, which I doubt anybody is here, but it's, again, at the end of the day, infrastructure changes things. So if you can build greener, more sustainable infrastructure, push for or lobby for renewable energy sources, that will really help with making our research more sustainable. Again, going back to, we really need to share more process data. And for that, you need to be able to discover that data, share that data, and also reuse that data across institutes, again, making a case for open science again in a different way. But that would really help. Just for food for thought, as we are into AI research, AI era, I guess, AI is going to get cheaper and more prevalent, so we all going to use. So for just not neuroimaging pipelines itself is not maybe it may not be the biggest problem in future, but actually the LLMs or other AI tools that we are using. Again, there's a rebound effect I talked about earlier. So we have to be cognizant about different AI modes, which is training versus inference and even interaction. So for example, all these general purpose tools that we use, we may not be training or even testing them directly, but we are using them, and the interaction with these tools has an impact. Many neuroimaging processing tools are also now using a lot of AI stuff. So there we might want to think about how to train these models, large-scale models or foundation models that we all want to build in neuroimaging in a more sustainable way. You might be familiar with many of these. Faster for sugar and deep prep have been very interesting and very useful models, but we should be just more cognizant of how we go about building new ones. I would like to thank Nick, who unfortunately is not here. Most of the work I presented here, he's the first author for those. Both Nick and Charlotte are part of the CSIC, which also I'm part of. It's the OHBM CSIC. So I would like to thank both Nick and Charlotte, who are in the University of Sussex, and my own lab, who has also helped me work on these projects, which is Origami Lab, JB Pauline, who's right there. We are in McGill in Canada. And just a small plug for a CSIC. So if you do care about climate change, which you all raised hands in the beginning, so I believe you all do care about CSIC, sustainability. We have a couple more things lined up in this conference. One is the silicon versus carbon, which is a typical trade-off we see between the two elements, or the battle of two elements, as we call them. It's on Saturday, on June 28th at 1 p.m. And we also have a booth. Please come talk to us. And later this year, we also have a satellite meeting, which will be held online in September. I think with that, I'm done. And I'm happy to answer any questions. If not, I think that concludes the first part, I guess.